Section 4.1, Basic Concepts of Probability. The single most important objective of this section is to learn how to interpret probability values, which are expressed as values between 0 and 1. A small probability, such as 0.001, corresponds to an event that rarely occurs. Next are odds and how they relate to probabilities. Odds are commonly used in situations such as lotteries and gambling. I think most people are more familiar with probability. The way I think about probability, probability equals part over total. I think a lot of people are comfortable with that. Odds, not so much. I look at odds as part to non-part. And I know students get confused by that, so let's look at a quick example. If you're rolling a die and you're trying to roll like a 6, let's say. Well, let's do a 5 because 5 is easier to draw, maybe. All right, we're rolling a single die and we want to roll a 5. Most everybody in this room probably knows the probability of rolling a 5 on a regular 6-sided die. Probability of rolling a 5 is 1 out of 6, right? Part over total, 1 out of 6. That's the probability of rolling a 5. But if I look at odds, in that same scenario, it's not as familiar to you because you're not doing part over total. You're more comfortable with part over total. This is part to non-part. So the way I look at it is how many 5s are there? 1. How many non-5s are there? 5. So the odds of rolling a 5 would be 1 to 5. The probability would be 1 to 6. Probability, again, is part over total. Odds is part to non-part. An event is any collection of results or outcomes of a procedure. A simple event is an outcome or event that cannot be further broken down into simpler components. And sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. I like to think of sample space as everything that could happen in this particular experiment. Example 1 talks about simple events and sample spaces. Give the sample space if we use B to denote a baby boy and G to denote a baby girl. Then find the number of simple events in the sample space. So for a single birth, the sample space is just what could possibly happen. Well, if you have one single birth, either it's a boy or it's a girl. That's it. There are 2 simple events inside of that sample space. There are 2 different things that could happen. And so the number in the sample space is 2. Now, if there are 3 births, it becomes a little bit more complicated. So the sample space is just what could possibly happen with 3 births. Well, you could have 3 boys, so I'm going to call that boy, boy, boy. Or perhaps the first 2 are boy and the third girl. Boy, girl, boy, girl, boy, boy. That's if there were 2 boys and 1 girl. Or there could be 2 girls and 1 boy. So you could say girl, girl, then boy, girl, then boy, then girl, or boy, girl, girl. And there's only one other thing that could happen. You could have all 3 girls. So girl, girl, girl. There are 8 different things in that sample space. There are 8 simple events in that sample space. So the number in S is 8. Just counted up the number of things there. We should already be comfortable with most of this. Probability is definitely going to be a number in between 0 and 1. And here's our notation for probability of some event A. Probability of A. Probability of rolling a 5. Probability of getting a tails on a coin flip. And we know that if that number, if that probability is 1, it is 100% certain to happen. If a probability is 0, it is impossible. It's not going to happen. And anything close to 1 is likely, close to 0 is unlikely, and 0.5 is right in the middle, 50-50 chance. Three common approaches to finding probability. Now, two of these I think make a lot of sense, but they seem very, very similar to each other. The third one's a little bit weird, but keep in mind probability is part over total. So number one is the relative frequency approximation. Conduct an experiment and count the number of times an event occurs. The way I look at it is if you flipped a coin 1,000 times and counted, all right, you counted the number of times that tails showed up. And if you flipped 1,000 times and tails showed up 502 times, then you would say that probability is 502 over 1,000. That would be the relative frequency because we actually did an experiment and counted the number of times it occurs. You look at that formula and it looks pretty much like the second formula, but there's a big difference. The first one, relative frequency, we do an experiment and we count the number of times we see something happen. Classical approach, the way I look at it is more like what we would expect to happen. If I flipped a coin 1,000 times, I would expect there to be 500 tails. And there's usually some kind of formula or something that we can calculate, or we look at some kind of theory, a theorem, and that's the classical approach. A keyword you'll be looking for later will be it has equally likely outcomes. Heads and tails are equally likely to happen. And then subjective, the probability of event A is estimated using knowledge of relevant circumstances. There will be certain times where we don't know how to calculate it, so we're just going to kind of estimate or take our best guess. So that's subjective. Being a numbers guy, being a math guy, I don't really like this one. Okay, I like formulas and I like plugging numbers in. This subjective is just kind of give me your best shot, give me your best guess. When none of these three approaches will work, we may use a simulation like a coin flip or a random number generator, something like that. Simulation is a process that behaves in the same ways as the procedure itself so that similar results are produced. Probabilities can sometimes be found using a simulation. We'll talk more about that in a later section. Rounding probabilities. When expressing the value of a probability, either give the exact fraction or decimal, or round off final decimal results to 3 significant digits. In general, I think you should write your answer so that it's the most descriptive it can be, okay? If you get some kind of crazy looking fraction, notice it says suggestion, when a probability is not a simple fraction such as 2/3, express it as a decimal. If you got some number like 993 over 1214, if that's your probability that you found, okay? To me, I would rather look at it as a decimal. And so you might take your calculator and say, all right, 993 divided by 1214 is 0.818. And so to me, my question is always going to be, which is easier to look at? Would I rather look at the fraction or would I rather look at the decimal? And sometimes it'll be one and sometimes it'll be another. If it's a nice, easy fraction like 2/3, we might rather just write 2/3, okay? 1/2, we like that. But crazy looking fractions, we're probably going to want to use the decimal. The law of large numbers states that as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. Let's say you flip a coin 10 times and you observe 7 tails. Okay, so the probability of tails, according to your experiment, would be 70%, right? 0.7. Now let's flip it 100 times, and this time you flip it and you get 55 tails. Okay, so now the probability of tails looks like 0.55. That seems more like what we would expect, right? Now we flip it 1,000 times, and we see tails 502 times. Okay. What's happening with this law of large numbers is that the greater this number is, the more times you flip it, the more likely it's gonna approach the actual probability. If you did it 1,000,000 times, it would be even closer to what we would expect of 0.5. That's the law of large numbers. Cautions. Law of large numbers applies to behavior over a large number of trials and does not apply to any one individual outcome. And two, if we know nothing about the likelihood of different possible outcomes, we should not assume they are equally likely. The actual probability depends on factors such as the amount of preparation and the difficulty of the test. I think that's a little bit difficult to read, so you might consider reading that again. Example 2, skydiving. In a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. So part A, I think, is a difficult question, perhaps, because you're not familiar with it. You might jump straight to part B, find the probability of dying when making a skydiving jump. I bet everybody in this room could find that probability off of this question, because we think about probability as part over total. But I wanted to make sure and highlight question A. Which of the three common approaches to finding probability would be best for calculating? So remember those three common approaches. Go back and look. Number 1 was relative frequency. Number 2 was classical approach. And 3 was subjective. So in this one, does anybody know which one of the three this is? I think that's a tough question, but this is relative frequency. And the way you can tell is because there's an experiment. There are 3 million jumps, and somebody's watching those 3 million jumps, and somebody is counting the deaths. That's what relative frequency is. You do some experiment over and over and over again, and you count the number of results, right? That's relative frequency. We can't use the classical approach because dying from a jump and surviving aren't equally likely things. That's kind of important for the classical approach. This is relative frequency. Part B, find the probability of dying from a jump. I like to write it like this. Probability of dying equals the number of deaths over the total number of jumps. But that's just part over total, right? It's 21 over 3 million. At which point you ask yourself the question, do I like the fraction, or would I think this would be better as a decimal? And to me, anytime your fraction looks kind of ugly like that, I'm looking at the decimal. 21 over 3 million. 0.000007. I like the decimal better. Now we got kind of a tricky result here because at some point before in the notes it said round off to 3 significant figures. But in my opinion, rounding off to 3 significant figures here doesn't give you a descriptive number. So I would rather have a number that describes my answer. I don't think 0.000 is going to cut it. So I'm going to keep all of those digits because that's a better descriptor, I think. Number 3. 3 children of the same gender. A family has 3 children. Assume boys and girls are equally likely to be born. We'd like to just jump straight down here, find the probability that the 3 children are of the same gender. But I'm asking you this question on purpose. Which of the 3 common approaches would be best? I think the key here is when you see this phrase, equally likely. All right. We're gonna look at this and we're gonna be able to calculate this. We're not actually gonna do an experiment and count. We can figure this out based off of they're equally likely. So which one is that? What's that called? Classical approach. And again, the key here for me is when it says equally likely. But also, it's not an experiment. I'm not looking at something. I'm not counting something. So it says find the probability that the 3 children are of the same gender. Let's look at the sample space again. And we already did the sample space for this scenario. 3 babies are born, and either they're all 3 boys or 2 boys or 2 girls or 3 girls. That's the sample space for this problem. So just think about probability as being part over total. The part that I'm looking at same gender, right? Probability of same gender. So they're talking about either 3 boys or 3 girls. 3 boys or 3 girls. And so this is part over total. I see 2 of those over 8 total. 2/8, of course, reduces to 1/4. I think that's a better answer. If you want that as a decimal, you can say that's 0.25. Out of these 3, they're all right. I think probably 1/4 is the best of the 3, but they're all the same. They're all equal. So I think any of them could be right. Typo. I didn't see that before. It's Katy Perry's money. Example 4, Katy Perry's money. What is the probability that the next dollar bill you spend was previously spent by Katy Perry? Okay, kind of a strange question there. I think it's obvious which of the 3 common approaches. This one has to be subjective. I'm not going to be able to calculate this. I can't do any kind of experiment and start spending dollars and say, nope, that one wasn't. Nope, that one wasn't. Nope, that one wasn't. I think it's subjective. There's no way really to calculate this. Just going to have to give our best guess. So I don't know. What do you think? 1 in a million? No real way of verifying it. We might be right. We might be wrong. We might be way wrong. But we're just going to have to try to guess. One in a million. Do we want to think about that as a decimal? Maybe. I'm not sure which one of those is better, the decimal or the fraction. They both are roughly the same. 5, texting and driving. In a study of high school drivers, it was found that 3785 texted while driving and 4720 did not. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. Okay. The textbook makes kind of a deal about not just jumping and throwing down answers. Okay. So I think they're saying you've got 2 numbers here. Don't just hurry up and make a fraction out of those 2 numbers and say that's the probability. Probability has to be part over total. So you got to really think about what the numbers are saying. This is saying 3785 texted and 4720 did not. So they didn't give us the total. They didn't give us the denominator for our fraction. In order to do that, we just need to add those 2 numbers together. 3785 plus 4720 is 8505. That's the total. And so if I want to find the probability that they texted, I want to do the part that texted over the total. So I would say 3785 over 8505. And so again, to me, the question becomes, do I like that fraction? Am I okay with that? Is that easy on the eyes, or would I rather look at a decimal? And to me, I would much rather look at a decimal here. 3785 over 8505.445. So approximately 0.445. To me, that's much easier to process. I can see that it's less than 50%. Yeah, that makes sense because this is less than 4720, so my answer should be less than 50%. Complement of event A. We've got some new notation here, A bar. Complement of event A consists of all outcomes in which event A does not occur. So, think about this. Let's say event H is you're wearing a hooded sweatshirt right now. Okay? Raise your hand if you're a member of event H. Okay? So if H is hooded sweatshirt, then H complement would be not hooded sweatshirt. So raise your hand if you're in the complement of that event, not wearing a hooded sweatshirt. Okay? Either you are or you're not, right? Either you're wearing a hooded sweatshirt or you're not wearing a hooded sweatshirt. The complement is everybody else, basically. You got some event, and then you've got everybody else. So the complement rule says this. It says the probability of some event plus the probability of its complement is 1. And that should make perfect sense because you should have, everyone in this room should have just raised their hand. Either you are wearing a hoodie or you're not, right? We got 100% of the people. And so the probability of an event plus the probability of its complement is 1. Maybe a better way of looking at this formula is like this. Probability of the complement is 1 minus the probability of some event. Those two equations say the same thing. I think the second one is probably more useful more often. Number 6, the complement of death from skydiving. In a recent year, there were 3 million skydiving jumps and 21 of them resulted in death. Find the probability of not dying when making a skydiving jump. Okay. So we're finding the probability of not dying. So according to the complement rule, it's going to be 1 minus the probability of dying. Or if you want to use symbols, I guess we could say something like this. We already did kind of the most important part of this problem. We did the probability of dying. We said that was 21 over 3 million. So this is going to be 1 minus 21 over 3 million. I'm definitely using the calculator here. 1 minus 21 over 3 million. 0.999993. And that makes sense because remember the answer before was 0.000007. So of course, when we subtract, we're getting 0.999993. Complement. Now, incidentally, we don't have to do this with the probabilities. We could say, well, there were 3 million total and subtract the 21 that die. That means there are 2,999,979 that didn't die. So if we took that number over 3 million, we should get the same thing. Okay, so I'd rather probably use the complement rule with the probabilities, but you can do it with just the regular number of items. To me, this right here is the hardest slide in the entire section. Identifying significant results with probabilities, the rare event rule for inferential statistics. If, under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. Okay, so if some probability is, you know, really small, like let's say, what's the probability of the next dog you see has 3 legs? Pretty small, right? And then somehow you go out and you see the opposite of that. You see like the next 10 dogs in a row all have 3 legs. There's something wrong. Okay, there's something wrong. Maybe there's something wrong with your assumption. Now that example is kind of absurd. I get it, but that's kind of what that's saying. If you know that the probability is supposed to be small, but then you observe it and it's way off from that, go back and check your assumption. And then there's this. Using probabilities to determine when results are significantly high or significantly low. I think you should just read this yourself. I think if I read this to you, your eyes are going to glaze over. Okay, so the key here is this 5% number. When you get to this question in your homework, it has something to do with 5%. Okay, if it's more than 5% away, I guess, that's significant. So you want to be, you want to look for this number 5%. Okay, so read through that. Probably going to need to read through it a couple of times. It's not going to help if I read this to you. All right, so we're looking for 5%. Now let's talk about odds. Probabilities make calculations easier, so they tend to be used by mathematicians and statisticians. Odds make it easier to deal with money and gambling, so they are used in casinos. So remember, when we talk about odds, we're talking about part to non-part. Not part over total. That's probability. Odds is part to non-part. So odds, actual odds in favor. So think about the odds of some event. Bless you. We can think of it as the number of items that do that compared to the number that don't do that. All right, in my previous example, I talked about hooded sweatshirts. All right, how many of you are wearing hooded sweatshirts? All right, that's a lot. Let's say that's 12. How many of you are not wearing hooded sweatshirts? Okay, that looks like 6. So the odds would be 12 to 6. 12 over 6, you can always reduce. You always want to reduce whatever your fractions are, but that's it. Okay, now we could interchange this with probability and talk about probability. We could do the same thing. The probability of an event over the probability of the complement of that event. Either way, whether you do the number or the probability, it still adds up to 100% of the items. Now let's talk about the actual odds against. Oops. If you're calculating the odds against, it's going to be the number in the complement over the number in the actual event. It's basically upside down from before. The way I like to look at it is, if you think about odds against A, think about that. Like this, odds of the complement. I mean, that's really what we're talking about. If you think about it in this way, it's the same. It's the same formula. Whatever you're looking at is on the top of this fraction or the top of this fraction. Probability of the complement over probability of the event. That's your odds against, your actual odds against. Now the payoff odds, okay, the payoff odds against event A occurring are the ratio of net profit if you win to the amount bet. Payoff odds against event A equals net profit to the amount bet. So what's tricky here, I think, is we've got actual odds and we've got payoff odds. And the reason we've got two different sets of odds is because if you go gamble, if you go to a casino, or if you go to some kind of charity event where they've got a casino night or something like that, they'll change the odds to tilt in their favor. The house always wins. The odds are such that the casino is always going to win a cut. Even if you win, when everybody plays long term, the casino's going to win money. They're always going to win money. And so the actual odds and the payoff odds aren't necessarily the same thing. Which brings us to example 7, actual odds versus payoff odds. If you bet $5 on the number 13 in roulette, your probability of winning is 1 over 38. We probably should look at a roulette wheel. I bet some of you in here aren't familiar with that, so let's just look it up real quick. Okay. All right, it's hard to tell here, but if you look at a roulette wheel, I know that's kind of small. The biggest number here is 36. The numbers go from 1 to 36. Actually, they go from 0 and double 0 up to 36. So that means there are 38 spaces in this thing, okay? From 1 to 36, it looks like, I was going to say evens and odds. It doesn't really matter, I guess. Half of the numbers are red and half of the numbers are black out of those 36 numbers, but then there are also these 2 green ones. So there are 38 spaces for that ball to land in on a roulette wheel. And so it would make sense that if you bet $5 on the number of 13, your probability of winning is 1 out of 38. That should make perfect sense, right? And so then it says, but the payoff odds are given by the casino as 35 to 1. All right? We would expect the odds to be slightly different than that. Okay? Those are tilted in their favor, so they will win. Now, I think you can probably do this without a formula. You can probably do this in your head, because if this is part over total, the easiest way to do this is saying, okay, the part that I want, there's one of them. There must be 37 others, right? There are 37 non-parts or 37 losing slots. So the odds against the outcome is gonna have a 37 in it for sure. Okay, so I guess the question is the 37 on the top or on the bottom? So maybe you know this, but let's look at the actual formula. If I said the odds against getting a 13, that's what the question says. Find the odds against an outcome of 13. I think I would rather write it like this. We're finding the odds of everything else, the complement of getting a 13. And so to me, once you've got that, then the formula is pretty easy. You can go the number of not 13s over the number of 13s. That's probably what I would do. There are 37 non-13s, and there's only one 13. So that's your actual odds. I think it probably makes sense to write this in this way, 37 to 1. When I see a fraction, I think about reducing that fraction to 37. I don't think you want to reduce that fraction, so you'd leave it as 37 over 1. Notice if instead of using a number right here, we use probability. If we said the probability of not 13 over the probability of 13, the probability of not 13 would be 37 over 38, and the probability of 13 was 1 over 38. You're going to get the same thing because those 38s cancel out. Doesn't matter if we use the n or use the p. Okay. Next, how much net profit would you make if you win by betting $5 on the number 13? So how much would you make? Remember, the casino's odds were 35 to 1. That was the casino's odds from the problem, right? Payoff odds, 35 to 1. So let's write that as a fraction, 35 to 1. And we want to know what's our payoff if we bet 5. So it's just a simple proportion. We can cross multiply to solve. We're multiplying 5 times 35. 5 times 35 is 175. Okay. Now, I think it helps to understand what we're talking about. This number is the net profit, and this number is the amount bet. Okay. I think it's important that we understand that what we just found was the net profit, and that's what they're asking for, the net profit. Okay. Our net profit is $175. Now, the reason I made a deal about that is because there's another number that I could possibly ask you for. You know, how much money did you pick up off the table? Okay, how much money did you actually collect? Well, we'd actually collect 180 because we would get our $5 back. Our $5 bet, we would get that back plus our 175 profit. So we're actually collecting 180, but the answer to this question, the net profit, is 175. Part C, if the casino was not operating for profit and the payoff odds were changed to match the actual odds against, how much would you win in that same scenario? Well, we found before that the odds were 37 to 1, right? So they're saying in this case, let's just use that 37 to 1. Let's use the actual odds and recalculate. So again, we've got a simple proportion. We're going to cross multiply to solve. X equals 37 times 5. 37 times 5 is 185. So we just found a net profit of 185. That's your answer. Keep in mind that we would collect 190. That's the profit plus our initial $5 bet.